Hi, in this talk, we'd like to present our work, a faster exact algorithm to count X3SAT solutions. So this is a joint work with Sanjay, Jain and Stephan. Now, as part of the introduction to this segment of the video, we would like to first explain what our problem is, followed by the results of our work. So, given a propositional formula phi in conjunctive normal form with variables x1 to xn, a well-studied question is to determine what values can I assign to each of these xi such that phi evaluates to 1. Now, this is also known as a satisfiability problem or SAT. This is the first NP complete problem as shown in Cook in 1971. Now, because of its importance, many other variants of the satisfiability problem has also been studied. Now, one such important variant is known as the exact satisfiability problem, or XSAT. It asks, can we find a satisfying assignment such that each clause has exactly one literal set to 1 or true, and the rest are set to 0 or false. In addition, if we restrict the length of each clause to having at most 3 literals, then the problem is known as the exact 3 satisfiability problem, or X3SAT. Now, XSAT and X3SAT are both known to be NP complete. So those problems that are mentioned above are what we call decision problems. Sometimes we are interested in the counting variants of such problems instead. For example, we can add a hashtag to the problem in front, and in this case we call it sharp X3SAT or counting X3SAT. And basically it asks, given a propositional formula phi with n variables, having each clause restricted to length at most 3, how many exact satisfiable assignments can we find? So model counting has diverse applications in the field of AI. For example, in Bayesian belief networks and probabilistic inference. So for this talk, we will be focusing on the problem counting X3SAT instead. Now, note that both counting XSAT and counting X3SAT are considered to be sharp P complete. In other words, these problems are considered at least as hard as their NP complete counterparts. So in this talk, we would like to present an exact algorithm to solve counting X3SAT in O 1.1120 to the n. Now, we basically improve upon the earlier author's work. So if you're interested, please stay on and find out the more technical details as we proceed to the next segment of the video. Welcome back to this second segment of the video. So over here right now, I will talk about the previous works done by the earlier authors. Next, I'll talk about some preliminaries and terminologies that we will be using for this talk. Then I will talk about the high-level sketch of the algorithm, followed by its analysis. And finally, I'll end off by giving a summary and also talking about the future work. So now note that counting X3SAT is just a special case of counting XSAT. Therefore, one may use any counting XSAT algorithm to solve counting X3SAT as well. Now the following list are improvements made to solve counting XSAT. And these improvements are done in the form of an exact algorithm. Now let n denote the number of variables in the formula. So trivially, one can solve counting XSAT in O 2 to the n, that's via a brute force algorithm. Next, Darloff and Johnson gave an algorithm to solve counting XSAT in O 1.7548 to the n, and that's via a reduction to the counting maximum independent set problem. Next, Portion gave an algorithm in 1.3248 to the n, and his version has weights attached to the variables. Next, Darloff, Johnson, and Bagel gave an algorithm in O 1.2190 to the n. And finally, Zhou, Su, and Wang gave an algorithm to solve it in 1.1995 to the n. On the other hand, it is possible to take advantage of the structure of X3SAT to solve counting X3SAT in a much faster time. So Darlow, Johnson and Bagel, in their same paper, they gave an algorithm to solve counting X3SAT in O 1.1487 to the n. In this paper, we build upon the previous author's work, which is Darlow, Johnson and Bagel, and we will improve the current bound to O 1.1120 to the n. So right now, I will first talk about some definitions that we will use throughout the paper. Now, two clauses are called neighbors if they share at least a common variable. Two variables are called neighbors if they appear in some clause together. We say that a clause C is a degree k clause if C has k neighbors. A variable x has degree k if it appears k times in total as the literal x or negated x. Now let's see an example. Suppose we have the clauses C1 containing x, y, z, C2 containing x, a, b, and C3 containing y, a, c. Then all three clauses are degree 2 clauses because for each of the clause it has exactly two neighbors. Variable x has degree 2 because it appears in C1 and C2. Next, we call a sequence of degree 2 clauses C1 to CK, k being at least 1, and we call it a chain if for j being at least 2 and at most k minus 1, Cj is a neighbor to both Cj minus 1 and Cj plus 1. So therefore, Cj is a neighbor to the clause before it and after it. Now, given any two clauses, Ce and Cf, they are at least degree 3, we say that these two clauses are connected via a chain if we have a chain C1 to Ck such that C1 is a neighbor of Ce or Cf and Ck is a neighbor of Cf or Ce. Moreover, if we have a chain of degree 2 clauses from C1 to Ck and S at C1 itself, then we call this a cycle. Suppose we have a degree 3 clause, for an example, ABC, and another degree 3 clause containing STU, and we have the following chain, CDE all the way to QRS, and we say that the clause A containing ABC and the clause containing STU are connected via the chain. So here we'll give some graph definition because a segment of our paper requires some results, some graph theoretic results. So let G be a simple undirected graph. A balanced bisection is a mapping pi from V to the value 0 and 1 such that we have two sets of vertices that contains the map value of 0 or 1 based on this mapping. Now the sets V0 and V1 have cardinality differing by at most 1. Now we let the cut of this mapping be denoted as the size of the set of vertices such that for these edges, one end of the edge lies on V0 and the other end of the edge lies in V1. Now the bisection width of G is the smallest cut that can be obtained for a balanced bisection. So here is where we'll be using a result by Monin and Priest. For any epsilon greater than 0, there is a value n depending on epsilon such that the bisection width of any three regular graph G having the set of vertices greater than n depending on epsilon is at most 1 over 6 plus epsilon times the set of vertices. This bisection can be found in polynomial time. Now also take note that the result by Monin and Priest can be extended to graphs having degree at most 3. So next here is where we'll give a high level sketch of our algorithm. We call our DPLL algorithm or branching algorithm count X3SAT, and basically it takes in 4 parameters: the propositional formula phi, cardinality vector C, two sets L and R. So the cardinality vector C has all the literals set to 1 at the start. The sets of clauses L and R are there to help us to keep track of the different partitions after applying the result of Monnian and Priest. So the cardinality vector C helps us to keep track of the number of exact satisfiable models while we apply simplification and branching rules. And we update this cardinality vector along the way whenever we apply any of these rules. L and R are sets of clauses that we use to store the two partitions, and L is denoted left, R is denoted right, after applying the Monnian and Priest result as stated in the previous slide. So now let S of phi be denoted as the set of exact satisfiable assignment for phi. Given phi, cardinality vector C and L and R, which are set to the empty set at the start, our initial call to the algorithm would be count X3SAT, phi, cardinality vector C, and two empty sets. Now, the output of our algorithm is the summation for each exact satisfiable assignment in S of phi, such that we multiply the cardinality vectors of the literals that are set to true based on this exact satisfiable assignment. Now we guarantee the above invariant by dropping off the entries of the literal L and L bar whenever L is assigned a constant value. Then we multiply the returning recursive call by C of L if L is set to 1, or C or L bar if L bar is set to 1. So here's a high-level sketch of our algorithm. First, apply simplification rules whenever possible. Now, there are many simplification rules in our algorithm, and due to time constraint, I will not be able to list any of them. So therefore, if you are interested, please take a look at our paper. 2, if there is a variable x with degree at least 3, we branch it. If there are degree 3 clauses and the sets L and R are not empty, then we choose an HE to branch. If the sets L and R are not empty, it means we have applied the Monnian and Priest and we are in the midst of choosing an HE to branch. Otherwise, if L and R are empty and we still have degree 3 clauses, then we apply the Monnian and Priest result to get a bisection width, to get a partition L and R, and then we continue this step recursively. If there are degree 2 clauses left in the formula, choose any variable, we branch them. So in this high-level sketch of the algorithm, line 2 and line 3, they are branching rules. Here is where we have to analyze their time complexity because line 2 and line 3 contribute to the exponential time growth of our algorithm. The simplification rules and line 4 of the algorithm only take up polynomial time and therefore we will not talk about it. So first, we will state the time complexity of branching degree 3 variables. So the time complexity of branching variables with degree at least 3 is O 1.1120 to the n. So this is done via a case-by-case enumeration. Again, there are many cases, so due to time constraint, I will not be able to state any of them. Now, after dealing with this, all variables must have degree at least 2, which means that since we are dealing with X3SAT, counting X3SAT, each clause has at most 3 literals. Every clause must have at most degree 3. So next, we deal with degree 3 clauses. So here is in fact 1 over t of the algorithm. So what we're going to do next is we're going to construct a graph G of E, and we'll let each degree 3 clause in the formula phi be represented as a vertex in the graph G of E. Now, given any vertices VC prime and VC prime prime, I'm going to add an edge between them if any of the two conditions occur below. 1, if I can find a variable appearing in both C prime and C prime prime. So let's take a look at an example. Suppose we have degree 3 clauses C prime containing x, y, z and C prime prime containing x, a, b. Now we see that x appears in both clauses, and therefore in this case I will add an edge to BC prime and BC prime prime. So this h is basically represented by the variable x. Second condition, when C prime and C prime prime, they are connected via a chain of degree 2 clauses. So for example, we have two degree 3 clauses C prime containing A, B, C, and C prime prime containing S, T, U, and we have the chain of degree 2 clauses C, D, E all the way to Q, R, S. Then in this case, we'll connect BC prime and BC prime prime by an H. And therefore, in this case, the H is represented by the chain of degree 2 clauses in this case. So now by construction, we see that G of E has maximum degree 3. And therefore, we can safely proceed to apply the Monin and Priest result to give us a bisection width. We branch the variables represented by the H in the bisection width, and we recursively do so until no degree 3 clauses are left in the formula. So now based on this bisection width, we choose an H to branch. The edges can be represented either by a variable or a chain of degree 2 clauses as mentioned earlier. So now if it's represented by a variable, we branch that variable. If the H is represented by a chain of degree 2 clauses, so here's where we're going to alternate the branching between the variables that appear in the degree 3 clause and a degree 2 clause at both ends. So let's take a look at one example. So in the same example earlier, suppose I have two degree 3 clauses, C prime and C prime prime, and C prime equals to AB containing ABC, C prime prime containing STU, and we have the chain of degree 2 clauses CDE all the way up to QRS. So now note that the variables C and S, both of them appear in the degree 3 and the degree 2 clause at both ends. So what we're going to do is we'll alternate the branching of such variables whenever this case arises. Okay, so right now what we're going to do is we will analyze the time complexity based on these two scenarios given earlier. So now one common way is to count the number of variables that needs to be branched, say k, and then we have the bound of O 2 to the k. However, if we were to use this method, this will give us a worse time bound, and therefore we have to approach this analysis differently. So one way is to use the branching factor method instead. Now, note that the cut size is bounded above by the cardinality of the vertices times 1 over 6, which therefore is the number of degree 3 clauses times 1 over 6. So now as we remove or we branch all the edges in the bisection width, the graph becomes disconnected and we can solve each component independently. So therefore it suffices to just fix our attention onto one of this partition and then analyze the complexity from there onwards. Now for bookkeeping purposes, for each edge removed in the bisection width, we can count an additional 3 measure, and we can see this by taking M3 divided by 2 divide by M3 over 6. So because in the bisection width there is at most M3 over 6 edges, and each edge will contribute to 3 additional measures. Therefore, the time complexity of dealing with degree 3 clauses is at most O 1.1092 to the n. Now how can we do this? We fix the effect of branching a variable on one of the partitions, say the left, and we just fix on the left side. On the other hand, we can also factor in the bookkeeping process, and we add an additional 3 whenever an edge is being removed. So therefore, if the edge chosen represents a variable, then the time complexity of doing so is O 1.0983 to the n. If the edge chosen represents a chain, then the time complexity is O 1.1092 to the n. Therefore, the worst case time complexity for this case is O 1.1092 to the n. Now let's give a quick summary. So in this case, we give an exact algorithm to solve counting X3SAT in O 1.1120 to the n, and the bottleneck of our algorithms comes from branching variables that are at least degree 3. So the novelty of this work really lies in the use of the Monod and Priest result, the construction of the graph, as well as a different way to tighten the analysis when dealing with degree 3 clauses. Our algorithm can be in fact extended to solve counting X3SAT with weights given to the variables in the same amount of time. Therefore, with this, I will end my talk. Thank you.